U substitution. So U substitution is a pretty important topic in calculus. So far we've only been dealing with integrals where we have kind of a basic polynomial, like x to the 5th or 2/3 x to the 1/2 minus x squared. We haven't had a function inside another function. And we talked about how we don't have a product rule, we don't have a product rule and quotient rule. And so what we're looking at today is problems where, like, for example, one here, it's a product, but what do we do with that? How do we handle that? Because before, when we had something like this, we said, hey, well, let's just multiply that in, and then we could take our antiderivative from there. But here, if I try to multiply these together, we are not able to do so. We would have 2x plus 3 times x squared plus 3x to the 1/2. I cannot just distribute that 1/2 in. And because these are not the same base, I can't do anything with my exponents if I them together. And I cannot take this 2x plus 3 and multiply it by my x squared and 3x because it's being protected by that 1/2. So what do we do with that? So what we're looking at today is U substitution, which is a technique, an integration technique, that allows us to integrate problems like this. And so we talked about this a little bit during Stinger. We can see that in this first example here, we have this piece, the 2x plus 3. And then we also have this piece, square root of x squared plus 3x. And this piece, x squared of x squared plus 3x, that's a composition of function, right? It's a function inside another function. And we talked about during Stinger how if I were to take the derivative of my green piece here, that would give me my yellow piece. Derivative of x squared plus 3x is 2x plus 3. So when we have an integral in this format, where we have that inside piece, so a composition of functions, its derivative is being multiplied, it's being represented there. Then I can do this technique called U substitution, where I essentially rewrite that inside piece as a new function, U, and then we integrate with that. So I know we already know the answer from Stinger, but let's see how we get that on our own. I'm just going to clean this up a little. Okay. So we know what that means. All right. So at first, you'll be like, Ms. Margaret, this is really weird. I don't know that I trust you with what we're doing. I promise I'm not lying to you. But stop me if you have questions along the way. It's kind of weird. It's really not a bad process, but it's a lot to take in at first. So let me know if you have questions along the way. All right, so the first thing we want to do is identify what are we going to let U equal. And typically, we want U to be that inside function. What is that composition? So here, I'm going to let U equal x squared plus 3x. If I take a look at my integral here, I can see that my composition, the piece that is a composition of functions, is the square root of x squared plus 3x. This whole thing here is a composition of functions. So I want U to be that inside piece. So I'm going to let U be x squared plus 3x. Just the inside piece here. X squared plus 3x. And I don't like that it's just says U equal. Let's let U equal. We'll write it out. Because we're choosing what we want U to be. Alright, now what we're going to do next is take the derivative of U with respect to x. So the derivative here, du dx. What's the derivative of x squared? Derivative of 3x plus. Do we agree with that derivative there? And now what we're trying to do, if we can look here, we see that everything is in terms of U du. Whereas in my original here, I see that everything is in terms of x dx. So I'm trying to translate everything to be in terms of U. Steve?
Do we not need the plus c?
No. So remember, plus c comes from when we integrate. Right now we're just taking the derivative. We will be throwing that in when we integrate that. Alright, so I want everything in terms of just U. So I'm going to go ahead and multiply by dx on both sides. So I have that du equals 2x plus 3 dx. Because again, I just want du. I don't want du over dx. Alright, so what we're going to do now is we're going to rewrite this integral, filling in those pieces in terms of u. Okay. So I'm going to rewrite this integral. Let me redo my highlighting here. If I look, do you agree that this piece here, the square root of x squared plus 3x, we could just rewrite as the square root of u? Square root of x squared plus 3x, I could just rewrite as square root of u. Are we good there? Okay. And then if I look, 2x plus 3, 2x plus 3 dx, isn't that just, whoops, I didn't want to do it on that one. Isn't that just du? 2x plus 3 dx, isn't that just du? So are you okay with me then just writing du here? I'm replacing the yellow with du, and I'm replacing that inside green. Are we good there? Means that you're looking at me.
Do you get to just choose what the u?
We do get to choose what the u is, but we will be choosing carefully. So, because I could have said, let u be 2x plus 3, but you would find that that doesn't actually help us out. So, if I were to have chosen let u be 2x plus 3, du would just be 2 dx. And when I go to substitute in, then I still would have had some x's within my integral here. So if I would have tried to substitute in here, I would have had, all right, well, that first piece is u. This is still square root of x squared plus 3x. Dx, it would be like du over 2. See how we still have x's within there? We're trying to get everything in terms of u. So this would be what we don't want to choose. So when we're choosing our u's, guys, we want to look to see what is that inside of our composition of functions. So first look to see what is my composition of functions. I can identify that here. So I want you to be my inside. Also, we should see that the derivative of the inside is represented somehow within my integral. So we can see the derivative of that green is that yellow. See?
So you always want the u to equal the composition.
Yeah, that inside piece of the composition. Mm-hmm. And the reason why we're choosing to do that is because we know that chain rule is what causes this yellow to show up. So we want it to be that inside, because when we do the derivative of the inside, we counteract that chain rule. Thank you. Oh my goodness, that was super fast. Thank you. That was like half an hour ago I put that in there to be done. I'm impressed. Okay. Other questions on what I've done so far? So again, as Musa asked, we are choosing what we want you to be, but we're choosing wisely. We want to choose that inside piece of our composition. And that's kind of the nice thing with U sub is if you choose the wrong thing, you'll find when you try to substitute into your integral, you still have pieces left over, so you chose the wrong thing. So with that being said, we never want to have an integral that has both u's and x's in it. It should all be in terms of x, or all be in terms of u. All right. Well, this we do know how to integrate. I'm going to go ahead and rewrite this. But we know how to integrate this. So we're integrating u to the 1/2. What's my antiderivative? What's my new exponent? The 3/2. Divide by 3/2, I'm going to multiply by my reciprocal. And what else do I need? Plus c, yeah. It was an indefinite integral, so we need that plus c at the end. Alright, so this green and yellow here, kind of crazy. We used U substitution to bring it down to something much more manageable. And now we have integrated it in a much more manageable way. But we started off in terms of x. I need my final answer to be in terms of x. So all we have to do is just take my x and put it back in. So I'm going to take this, which I did over here, and put it back in. So I have 2/3. Instead of u to the 3/2, I'm going to take my u, which was x squared plus 3x. And this is my answer there. Compare it with Travis and SB3's answer. Questions on what we just did? Tony, are you good? Good. So again, kind of a weird thing. Not too bad, a lot of stuff that are happening here. And we're going to be doing multiple examples with this so we can kind of get the hang of it. Are we good before we move on to another example? Yes?
So how did you go from the integral of u to the 1/2 down to the 2/3?
I just did normal integration. So my inside derivative, add 1 to the exponent, divide by your new exponent.
Okay.
Plus u. So we're now just doing normal integrations, just instead of my variable being x, my variable is u. Instead of my variable being y, my variable is u.
Okay.
Other questions? Good? Okay. So let's take a look at example 2. So which piece here is my composition of functions? Okay. So this guy here is that composition. So what should we let u be? Good. 5x squared plus 1. Alright. Now let's go ahead and do our derivative with respect to x. So we would get 10x plus 0. Now again, I want to have it just du equals, so I would have then du equals 10x dx. Be good there. Okay. So now let's make sure we have all of our pieces before we proceed and turn it into terms of u. So I have 5x squared plus 1 is u, and then I have 10x dx, which I have. So now I can go ahead and rewrite this integral. So instead of 5x squared plus 1, I have u squared, because again u represents that. And then 10x dx is just simply du. So I have the integral of u squared du. Alright, go ahead and integrate that. Let's see what you get. Here's what's going on. Are you good with my antiderivative? Okay. So now I'm just going to take my u and put it back in. 5 squared plus 1 u cubed. 3 plus c. That's my answer there. And again, remember, we can check to see if this is right. Let's do our derivative. If I bring down my 3, those reduce. 5x squared plus 1 quantity squared times derivative inside, which would be 10x. You can see that is represented. Questions? Are we good? A little hesitate because you know it's going to get harder. Okay. Now, nicely in these two problems, well, and here in example 2, our 10x dx was right next to each other. Whereas we can see in example 1, 2x plus 3 was not right next to your dx, so sometimes you have to look for those different pieces. But what can make this a little more difficult is sometimes we don't have everything we need for our du. And if you don't have everything, you should only be missing a coefficient. You should only be off by a number. You should never be missing a variable. If you're missing a variable or an entire composition or entire function, that means you chose the wrong u. But if I would have had 5x dx instead of 10x dx, we can work with that. Okay? So let's take a look at example 3 here, which we have to consider that. Before we start example 3, are you guys okay with me just going from here to here? When we take our derivative u, just writing dx on the end, because we're always going to multiply by dx at the end. So are you guys okay if I skip that step? All right. So example 3. Well, we don't really have a whole lot of options for you. What should we let u be? 1 plus 2x. So let u equal 1 plus 2x. So du would be 2 dx. Good there. Okay. So now, if I take a look at what I have in my integral, I have the 1 plus 2x. But if I look, I only have dx. I don't have a 2 there. I am missing this 2. I need that 2. Now, there's a couple of ways we can deal with this. I'm going to show you both ways. You do whichever way you prefer. It's really just doing some algebraic fancy footwork. So I need 2 dx. So I have my 1 plus 2x to the 4th. Instead of dx, I need 2 dx. So I'm going to multiply a 2 in there. But I can't just take a 2 out of thin air and throw it into my integral because I've changed the entire value of my integral. I've now doubled the value of my integral. And this is no longer equal to that. So how can I counteract multiplying a 2 in there? Yeah, multiply by 1/2. Because now my 1/2 and my 2. Well, what is 1/2 times 2? Just 1. And that gets me back to my integral. So now I have the piece that I wanted, and it still represents that same amount. Now, why did I choose to write the 2 in and the 1/2 out? Only because I needed the 2 for my dx, and 1/2 I didn't really need, so I just went ahead and remember coefficients we can just plot in front. So I just went ahead and put it out in front so I didn't have to mess with it. Are we good as to what I have done here? So now then I can go ahead and rewrite this. I have 1/2 the integral. This is just u, so u to the 4th. And this is just u. Are we good there? Okay. Now I'm going to pause. I know that we can finish integrating this, but I want to show you the other way that you can adjust this as needed. Okay, so I'm just going to do it here. So I'm still going to let u be 1 plus 2x, and du be 2x. Okay. So the other way that we could adjust this to make our integral match nicely is that, again, I see I only have a dx, but here I have 2 dx. So since I only have dx, I'm going to divide by 2. So I have du over 2 equals dx. Does that make sense what I've done? Or just simply divide by 2. Or you could think of it as 1/2 du. So now when I change my integral, I still have u to the 4th. And dx is simply du over 2. Which, when I rewrite that, I'm going to bring that 1/2 out in front. U to the 4th du. Notice it is the exact same thing as what I have there. Okay, so again, instead of bringing in what's missing from my dx, I simply solved for what I had, which I had a dx, and then I substituted that in. Questions on that method? And you can do either method. They take about the same amount of steps, whichever you prefer. And also, too, as you're working through this, you might actually want to rewrite this instead of d over 2. You might just want to rewrite it as 1/2 du dx. So when you go to put it in your integral, you know that constant can just come out in front, so you can just go and pull that out in front. That can save a little time. But again, either way. All right, so now let's go ahead and integrate. So let's see, I have 1/2. My new exponent is 5. I have to divide by 5. And then I have my plus c. So u to the 5th over 10 plus c. Oh! Or substitute back in. Are we good with this before I substitute my terms back in? Trevor, you good? Alright, so instead of u to the 5th, I'm going to actually put my u in. Over 10 plus c. And again, whether you do the blue method or that black method over there, you still do the same thing. Questions on that? Alright, so let's go and do example 4. Kind of a similar thing, where we're lacking pieces. Alright, what should be my u this time? What should we let u be? Good, 9 minus x squared. So du, what's my derivative of this? Negative 2x dx. Make sure you don't lose that. Alright. Now, again, I can see that I have already x dx. So I don't need that negative 2. So are you guys okay if I rewrite this negative 1/2 du equals x dx? I just simply divide it by negative 2 on both sides. Are we good with that? Okay, so I'm doing the black method over here. Alright, so now I can go ahead and rewrite that integral. This becomes square root of u, and x dx is just negative 1/2 du. So I'm going to go ahead and pull out that negative 1/2. So I don't have to mess with it. Are we good with that? Alright, go ahead and integrate that. See what you get. Do we agree with the green? Any questions? Feeling good? Suspicious? So again, here I did the method where we solved for the x dx since that's what we already had. If you were to do the other method, just this off to the side here, I would have needed a negative 2, so I would have gone ahead and multiplied. I would have multiplied by a negative 2 as needed, and I would have needed to counteract that with a negative 1/2. Then we have this whole thing here is du. I can rewrite this as negative 1/2 integral of square root of u du. And again, we're right back to square root. So that's how we get that negative 1/2. Okay, so again, whichever method you prefer. Okay. Let's go ahead and take a look at example. I want you guys to try 5 and 6. Multiple choice. Number 5 was from the 1993 AP exam. So I'm going to try 5 and 6 here, see how you do with that. Yeah. Well, what we're doing is, so for this method here, I need a 2, so I multiply by 2, and so the reciprocal of that would be 1.
Yeah.
So like, even if it was crazy, say that was 2/3. You multiply by 2/3 and counteract it by 4. So that's the reciprocal. Does that make sense?
What did you get with
The other way you end up solving for it, so
you subtract it, right now.
so like,
Can you get confused with the exponential?
so I have just like so divided by 1 and 2.
I keep getting confused.
And then that's
with the integral.
So if this one here,
Exponents, you know, like how equal equal 1 exponents. So you don't need to pass that negative.
so I would rest the video.
Yeah.
No, I keep mixing it. Increase the exponent.
Yes. that.
Yeah.
So the next one.
Okay. So that would equal,
And
and
then that would be
are you getting DU over U? I'll get that.
You gotta go use the negative.
Alright. I can't use these if it's on this.
You don't want to. No. Normally, the reason I want to is because we brought in that negative two. That's my shot with my name.
So the -1 has to move to the negative.
So when I reduce it,
Because 1 half means it's.
don't have.
Oh, yeah, this is.
So the whole reason why we also have negative two is so that I can have.
Did you do DU over that one?
Yeah, so
Did you do this
I
number?
wrote this first.
I don't know, that's what I wanted to show you.
What's the log? So then.
And then
Yep.
the X, or X.
Okay, so.
What would it be like?
It would be the, so you already brought that up.
Oh, that's right.
Which you can write it in and then set it aside for now.
Yeah.
Piece it together in one second. Got you.
Sounds like it would just like.
Yeah, and you just have two times.
So then U is actually plus 5, right?
To 9 minus X squared.
I got a.
So you're working with the whole reason why this is so it's easier to integrate. So first, you go on with given and substitute,
Oh,
right?
yeah.
Because we want to go this little bit closer, and then so you just for this, once you and then
When you guys think you have your answers, check with someone nearby you, see if you got the same thing. If you got stuck, say, hey, what's up? How'd you do this?
I love that game.
No, sorry, that's fine. You can save this.
So what are you gonna? I don't really.
Okay, guys, for number 5 here, make this a little bit easier on yourself. This is 3x squared times x cubed plus 1 to the -1/2 dx. Does that make sense? It might be a little bit easier to identify what you should like do for that, guys.
So I sent mine, so it was like, perfect. So it was like that's what the last one you're using. So what you do next is you just take, so you know this little problem, what system are you using? And then you take U and you substitute that, you're letting U equal that. And then DU, and then you're going to integrate this, so that's the.
I don't have enough details to do this.
And then you plug that in.
I need 3.
Yeah, it took me 8 minutes, so I was like,
Take Oh! If there's a single here.
It just seems wrong when you read the same.
I can't find it.
I got the second set and I think I got the first one.
Yes.
What was
Can?
you?
My U is x cubed. Plus 1. So what's the DU?
People see
I don't know.
I haven't got anything.
And then you just move like
You do it too.
and honestly, guarantee them all.
Okay.
So I was just wondering, I didn't go about it, and I was wondering what's the point of
So think about it in our original.
That's what we don't get.
Sorry.
Yes.
What?
Like, we never
What
plugged in
variable?
3x.
Okay,
You just tells us, hey, we're doing this with respect to you.
and now I'm
So just like
so,
All right, Joey asked a good question. He said, what's the purpose of this DU? So I'm just going to take a look at our last problem we did. He said, what's the purpose of this DU? Well, remember, that's just our differential. dx just simply tells me I'm integrating where x is my variable I'm integrating. And so when we change everything in terms of u, we want to be integrating with respect to u. Now, this might seem kind of silly because we've only ever integrated with respect to one variable, because this is single variable calculus. Those crazies that are taking multivariable calculus, they sometimes do a double or triple integral, where they would do it with respect to x. They'd have dx, dy, dz. That tells them which one to do what time. For us, it's just based on whatever. All right, what did we get for example 5? A. And example 6? Oh. All right, so a couple of things here. Let's just go ahead and real quick make sure we have the correct u and du. So for this, did we let u be x cubed plus 1? So then du was just 3x squared dx. Yeah. Okay. And thankfully, all of that was here. So when I rewrote my integral, I had then just u to the negative 1/2 du. Right? Okay, so then when I did my inside derivative, that would be u to the positive 1/2 multiplied by your reciprocal, and then take your u and put it back in. Are we good with 5? Any questions? Okay. 6 required a little bit more work. I'm hoping that we let u be x cubed plus 5, and du was then 3x squared dx. We agree? Okay. Now here I only have x squared dx, so I needed this 3, so you could have multiplied in the 3 and thus had the 1/3 in front, or divide by 3 on both sides, and we end up then my integral is that 1/3. Either way, then we have u to the 6th du. Do we agree with that? Anyone not good on that, or on that integral U substitution? Good? Okay. So then when we did our antiderivative, we had u to the 7th. Got by 7 times 1/3. So that gave us the 1/21st, and then our u substitution. Questions on that? Okay. So for example 5 here, you'll notice that a couple of these had natural log as part of the answers, which you're like, silly people, why would we even have natural log appear in here? The reason why is because in a couple of units when we learn about exponentials and logs, when we do our derivative and antiderivative, our derivative of natural log looks a little bit similar to this, but not really. So just be looking for that U substitution. Again, it's when you have a function inside another function. Okay, let's take a look. Go ahead and give example 10 a try. What do you think we should do before we even start? I would do a common denominator if those were it's even easier in common denominator though. If these were like two different fractions that we want to multiply together, this whole thing's very second power. What do we do anytime we have stuff in the bottom? Get rid of it, house. Can we just write this t to the negative first? So 1 plus t to the negative first squared times t to the negative second dt, right? Okay, do that, because you know how to do your derivatives and antiderivatives when negative exponent's better than when it's in a fraction. Alright, so give example 10 a try. Again, feel free to work with those around you. Let's see if there's another one.
Well, this is what I was doing all the first weeks.
Oh. Do you guys agree with my integral with the u? Regardless of which method you use, negative integral of u squared du. Any questions up to that point? So when I go to do my derivative here, it's negative t to the negative second dt. Are we good? That power comes down. Reduce the power by 1. So then I needed that negative. So I divide by negative on both sides and then the negative t. Does everyone see how we got that negative? Okay with that? Yeah. So my negative, guys, when I do my derivative of u, derivative 1 is just 0. Derivative t to the negative first. My exponent comes down. So I have that negative 1. And then reduce my exponent by 1. So negative 1 minus 1 is that negative 2. So then I have du equals negative t to the negative second. So that's bring the exponent down. So don't lose that negative there. Other questions as to how we got to this point? Either way, I wrote both ways for you. Okay. So then I would have negative, increase my power by 1, divide by 3, plus c, and just substitute it back in. 1 plus t to the negative first. Stick that for plus c. That's right. Questions on that? Okay. So what we've dealt with so far is just indefinite integrals. What does that mean to be an indefinite integral? No bounds. So if you notice, so far we haven't had bounds. Now that means that our answers will always be a function plus c, as we've seen so far. Now we're going to next do, how do we do definite integrals? Thus we have the bounds with U substitution. Sarah?
Does the negative not go to the c as well?
You could go ahead and distribute the negative to c, but a constant could be either positive or negative. So we just typically put plus c. If you had minus c, you'd still be fine. Because that constant just represents some value. That's a good question. Alright, so let's take a look at how this U substitution works once we actually tack on bounds here. It's still the same process, but what we have to consider now is that our bounds need to be in terms of u. Again, your entire integral either needs to be in terms of x or in terms of u. We cannot have a mixture of them. So now all we have to do is we have to actually change our bounds as well. So again, we still have this type of, this looks like chain rule, where we have that inside function and its derivative is represented. So now we have bounds. And so these bounds are saying x equal to a and at x equal to b. But when I change it all to be in terms of u, I can no longer have my bounds based upon x. So we have to find out when x is a, what is u? And when x is b, what is u? So we have to change our bounds here to be in terms of u. Alright, so let's go ahead with example 1. Again, still the same process, just we now have to deal with our bounds. So taking a look at example 1, what should we let u be? Good, x squared plus 1. I want to write it left. Oh, right. Okay. Alright, so let u be x squared plus 1. So then du would be 2x dx. Okay. Now, I need to go ahead and look. I see I have x dx. So whether you want to multiply in that 2 and 1/2, or just divide by the 2 here, whichever you prefer. So I have 1/2 du equals x dx. So again, this is what we've just done before. Questions on that? Now before I start substituting everything in, I need to also change my bounds. Because my bounds are based upon x. I want to know what are my bounds based upon. Alright, so we want to know what is my u value when x is 2, and what is my u value when x is 0. So I'm taking it from here. I know this is when x equals 2. Well, when x equals 2, what is u? Well, that's just simply taking 2 and putting it in for x. So when I take 2 and put it in for x, what do I get for my u value? Huh. And I have to do the same thing with my lower bound, because this is when x is 0. But when x is 0, what is u? 1. That's going to be my new bounds. Now you need to make sure you're careful that you replace the bounds properly, because we won't always have that the lower bound still yields a lower bound over here for my u's. Sometimes it does flip-flop around, so just make sure you're replacing the 2 with the 5 and the 0 with the 1. Okay, make sure you don't do this flip-flop. Okay, so now let's go ahead and rewrite our entire integral in terms of everything u. So now instead of bound 0, I have bound 1. And instead of upper bound 2, I have upper bound 5. And then again, this is going to be u squared. And x dx we said was just 1/2 du. I'm going to go and pull that 1/2 out. Questions on what happened there? We all good with that. Okay. So now we just do it like a normal definite integral. You can keep this 1/2 out. You can multiply it in either way. What's my antiderivative of u squared? U cubed over 3. And I want this evaluated from 1 to 5.
You have these brackets when you want to evaluate them.
That bracket indicates that we're evaluating. Sometimes you'll see just a vertical line as well.
And it doesn't include the 1/2.
We could go ahead and multiply that 1/2 back in because it is a coefficient. So like right now as I evaluate it, I'm just going to multiply that back in. You could keep it 1/2 out in front, but I need to have a big set of parentheses around everything. So I'm going to take my 5 substituted in, 5 cubed. So actually, I won't simplify too much. So we have 5 cubed over 6 minus, take my 1 and put it back in, 1 cubed over 6. Does everyone see how I got that 6 in the denominator? Again, I could have rewritten this instead. I could have kept the 1/2 out in front and said 5 cubed over 3 minus 1 cubed over 3. Does not matter. It gives us the same thing. But I would just went ahead and multiply together. I remember for response we could stop right here. You could have stopped in this step, but it's probably multiple choice where they simplify. What do we get for our answer then? Ooh, 62 over 3. So we got 124 over 6, right? 125 minus 1. Divide that in half, 62. So again, same process. The only thing that changes is now we have to change our bounds and evaluate it accordingly.
So when you have bounds, you have to do the fundamental theorem. So like,
Yes. Yeah. Yep. So the fundamental theorem of calculus is when we have a definite integral where we actually substitute those values in. So notice we don't have a plus c because it's a definite integral, and we should end with an actual number or a series of numbers for first ones. Other questions? Okay. So let's try example 2. Alright, so let u be, what would you guys like?
x squared plus
Good, x squared plus 1. So du would be 2x dx. And that pesky 2 is in our way. So we have 1/2 du is x dx. Or again, you could have rewritten this as 2x dx, counteract by that 1/2. So again, either way, whichever method you want to use. Are we good up until this point? Now we need to have our new bounds. You should not ever write an integral in terms of u with x bounds. If you're mixing x and u's, and it's going to be wrong. So I'm going to go ahead and maybe. So I need u of 1, u of 0. Again, be very careful as we're replacing our bounds here. When I take x equal to 1 and put it in, what do I get? 2. When I take x equal to 0 and put it in, what do I get? Alright. So I'm going to take all that and assemble it into a nice integral. So we have the integral. My bounds are going to be 1 to 2. And x dx was 1/2 du. I'm going to stick my 1/2 out in front. Du. And then I just have u cubed. And that's my substituted integral. I want to make sure we're good there. Continue. Do we have questions so far? Are we good? Are we all right for me to move on from here? Is here you both?
No, I'm just doing this.
It's very nice. All right. So now let's go ahead and do our antiderivative. Again, you can keep that 1/2 out in front. I'm just going to go ahead and multiply it all together, though. It's, again, your preference. All right, so my new power is 4. I need to divide by 4 or just multiply by the reciprocal. So then I have, let's see, that becomes 1/8. So 2 to the 4th, 5 by 8, minus 1 to the 4th, 5 by 8. 15 eighths. Spells, yeah, I'm going to go with that. Questions on that? Again, for response, don't simplify multiple choice. And again, if you would have done this method over here, so what was that? So it's still in terms of x, I keep my bounds in terms of x. And then when I go ahead and rewrite my integral, this was du. And this is just u cubed with my new bounds. So whichever way. Alright, I want you guys to go and try example here on your own, and again, be careful that you replace the bounds properly. Try example 3. Feel free to work with someone next to you. Feel free to ask me questions. I'll see you guys. I'm going to go and throw up my work up here so you can compare. Yep.
Is there a point where you can drop a negative on the bottom?
I didn't know.
Did we get 1/3 for our final answer? Raise your hand if you got 1/3. Okay. Now, I did some slightly fancy, but not that fancy, but helpful math here. Does everyone see what happened from this step to this step? Because I suddenly dropped my negative, but why was I allowed to do that? Yeah, I flipped my balance. You didn't have to. The first time I did this, I just proceeded like normal. But that negative's kind of pesky because then we have a negative carried all along through. And it's nice to not have to deal with the negative. So I switched my bounds and negated it, which gave me a positive 1/2. And then I continued from there. So again, you could have left it like that. You still get the same answer. If you would have left it like this, you would have gotten negative 1/2 u to the 3/2 times 2/3. 2's reduce. 1, 2, 0. Which then would have given you 0 substituting, which is 0, minus 1 substituting, which is negative 1/3 times 1, which is just then positive. So you end up getting the same answer. Just fewer negatives have to deal with the next one. Questions on that one? Yes?
For the DG, how do you put negatives to that?
So when I do my derivatives, bring down your 2, so I have negative 2x, reduce my power 1 is x. We take the derivative of this whole thing. So derivative 1 is just 0, and then derivative of negative x squared, we bring the 2 down, negative 2x. Other questions on this one? What? Alright. Which one do I want you to Let's go and take a look at example 7. So it's multiple choice. 1973. This was before I was born, in case you were. Alright, again, rewrite this 0 to the 1/2 so that it's 2x times the quantity 1 minus x squared to the negative 1/2. Always start off by rewriting it. It helps to identify your u a little bit better. Makes it a little bit easier to take it. So give that one a go. See what you get.
Oh man, I made you do fractions. Bummer. They weren't too bad though.
What is Oh my goodness.
Alright, this should be your antiderivative, depending on whether you decided to negate and switch your bounds or not. So either way here. Are we good with that? So this is an either or, either the red where you did not switch your bounds, or the blue where you did negate and switch your bounds. So notice the red has a negative from 1 to 3/4. The blue has no negative from 3/4. Are we good with that question? Alright, what did we end up getting for our answer?
4 minus 3/2.
A, B, C, D, or E. So let's just real quick take a look at this. Raise your hand if you switch the bounds. So it looks like the majority, so we'll go with this term. So 2 times square root of 1 is just 1. Minus 2 times the square root of 3/4. What is the square root of 3? Square root of 3. What's the square root of 4? That's 2 times. So you simplify that. Questions on that? Okay. So your homework is worksheet 3-6. Whenever we didn't get to know this, just extra for you. That is not required for homework. Worksheet 3-6.
2 times the square root of
Where did he do that?
They're supposed to 2 minus 1.
Because you plugged it in.